we start?
Okay, good morning. She is Crystal Rodabaugh. She is a student from the math program department. She's a very good student, and she's going to graduate this coming May. She works in a very specific problem to solve a model for the West Nile Virus here in Colorado. It's one of the topics that is very difficult to work in a regular class. So she did an amazing research looking for information in CDC and in different research topics that we were working for almost 1 year until now.
Okay. Thank you all for coming. My name is Crystal, and again, as she stated, I'm doing a presentation on West Nile virus in Colorado. I'm going to provide you some tables provided from, or some numbers provided from the CDC website, which I have put together. Give you some histograms to see how human cases are distributed and what's happening with West Nile virus as it enters our population over the time span of 2002 through 2012. Okay, so West Nile virus made its first documented appearance in New York City in 1999, and it originated from Africa, the Middle East, and in Europe. And in New York City, they had 62 human cases with 7 fatalities. Now, the disease didn't enter Colorado until 2002. And in 2002, we only had 14 cases with no fatalities. But because of the new introduction to the disease into the state, we had no fight back. There's still no cure for West Nile virus for the human cases. So it's predictable that in 2003, even more cases are going to be present. And in 2003, as you can see, I have 2,947 cases with 64 fatalities. That is humongous. West Nile virus is basically, it starts within an infected bird. It hosts the disease. A mosquito will then bite into the bird, and it'll act as a transmission vector. And it'll carry the disease through its small lifespan, and it'll bite humans, and it'll transfer it through there. And so it's classified into 3 different categories. You've got a West Nile fever, which is not so severe. You've got the meningitis symptom, which can affect the person's nervous system. You've also got a clinical, where you just go into the doctor, you get tested for it, and you just leave the same day. It's almost identical to the West Nile virus fever. It's just those clinical are considered to be actually documented. So here from the CDC website, I have 4 histograms for you from the years of 2003 to 2006. If you look in the different time frames of July through early September, you see most of my cases are happening there. West Nile virus occurs in that specific area of the year because we've got more stagnant temperatures. We've got, it's a little warmer, or you're getting more humidity, and so mosquitoes like to breed in the stagnancy, humidity. The more humid, the more river waters, the better. So when you've got this increase in humidity and you've got these stagnant waters, you're increasing your mosquito population and thus increasing your disease vector. And so here I've created this table, and I got this from the CDC website, and this is from the years of 2002 through 2012. In 2003, note the 2,947 cases, and in 2007 we also had 578 cases, which is huge. And we go back down, we're going back down, our temperatures are declining, so our mosquito population's not producing as much. But in 2012, you see we go from, in 2011, to 7 cases to 131. If you haven't noticed this year, our temperatures are pretty high. And so this seems to be kind of a direct correlation to how many cases we're getting in Colorado. And here's a histogram of the 2012 cases. And again, like I said, in July through early September, you've got most of your cases happening in that region. Here from the CDC website, again, I have a county divided map of Colorado, and this is in 2012. You see that our Alamos is actually here on our 1. That was our case. And you see most of the numbers, the higher numbers, are over here in this, this region, and this is the Montrose region. And you have more mountains there, and therefore you have more rivers and more stagnancy, so there's more mosquitoes there. And so you've got more infections happening in that region of the state. Okay, so when we're modeling this disease, we're using epidemiology. And epidemiology is the study of the causation of these effects and of the effects towards a susceptible population. And so we use this SIR method. It's a compartment class method that divides your population into different categories. And so you've got a susceptible population, the S, you've got an infected population, the I, and you've got a recovered population, the B. And here I'm considering bird and mosquito populations. My mosquito population does not have a recovery class due to its small lifespan. It only has a lifespan of about a month, so therefore it will not recover from the disease. And this is basically what I forgot to get rid of that. That's okay. Okay, so I'm going to be showing you some differential equations that'll model the dynamics of this disease. I don't expect you to understand where these equations are coming from. I'm just going to show you that these are the equations we use. And this is the parameter definitions I've set up to better model what's going on with West Nile virus. So here, you'll see these values in my crazy model in just a minute. So here again, like I mentioned, I have 6 equations here. And just like any algebra class, you're solving systems of equations. That's what we're doing with these equations, is we're solving these systems to find some critical point. And we call these critical points equilibrium points. And so here I have these six equations, and this models the dynamics of West Nile virus in the bird and mosquito populations respectively. Now what I've done is 6 equations looks a little scary. So what we do with these equations is we reduce it. We'll reduce the system, and we normalize the system to 4. And I've done this, and so therefore we'll have 4 equations instead of 6. But what happens to the other 2? Well, there's some kind of relation when you go back. And we'll determine that relation later. But here's the system that I have that'll model my 2 different populations. And when I was talking about critical points, we want to look at equilibrium points. And so going into that, I have my disease-free equilibrium. And that's when I don't have the disease in my population. And so here you see my equilibrium point has 4 different little parameters, right? Well, that represents the 4 differential equations. I was able to reduce the 6 differential equations down 2. And what this means is that, as I've stated before, my S of B represents my susceptible bird population. And that means that the susceptible bird population is equal to the total population, my N sub B. N sub B represents the total population of birds. And if it's a disease-free equilibrium, I have no infected birds and I have no infected mosquitoes involved. And we want to look at this critical point because we want to determine whether the disease is going to produce an epidemic in the area or if it's not going to be epidemic, if it's just going to get rid of itself. So then when we're analyzing these diseases, we want to linearize the system around this point. And that's just a fancy term for saying I want to look at what's happening around that critical point. And the values I get around that critical point will determine whether I'm stable or I'm not stable. And so when we're talking about these critical points, the biggest thing in epidemiology, the biggest goal is to determine this reproductive number. This reproductive number is the number of secondary cases produced from a typical infected individual, and when it's introduced into a susceptible population. So how many of those individuals in that susceptible will become infected from the infectious individual? So we're going to consider different numbers for R naught, and I'm going to show you how these values are extremely important. So consider our reproductive number equal to 2. And say that we have 2 individuals in our population, say they're the birds, and we've got 2 of them infected, and they're in contact with 2 more people. That's my reproductive number. That's how many they're going to be in contact with. Now, as I go through time, those 2 individuals get infected, but the 2 I started with will become cured from the disease. But I've doubled how many people I've infected now. And so those people become in contact with 2 more people, and it infects more people. And as you can see, my disease spreads faster than what's actually being cured, or what's actually getting dissipated. So really my infecteds are becoming larger than what's actually being cured. And so this becomes a problem. This is what we call an epidemic. And so we want to look at, okay, so how do we avoid this? So let's consider R naught to be less than 1, and say we have these infected individuals. Well, if it's less than 1, then they're not really infecting more than 1 person, because it's less than 1, right? And so as we can see, as time progresses, our individuals slowly but surely become cured, and we've gotten rid of the disease. And so this is extremely important. When we're analyzing diseases, we want our reproductive number to be less than 1. If it's less than 1, then we're not at an epidemic. And so from this, we can determine, okay, at a general secondary infection. And so we say that from a secondary infection is generated from the typical infected, and when it's introduced into that susceptible population, it produces so many infected. And we want to keep it at less than 1. We want to keep that reproductive number less than 1 because then we're not in an epidemic and the disease will eventually just take care of itself. However, if we're greater than 1, we've got a problem and we need to figure out how we can get rid of the disease. So for my model, as I've said, I've looked at birds, and I've looked at two different species of birds. I'm looking at blue jays and American crows. They're very abundant in Colorado, but they're also susceptible to the disease. Here, I'm going to show you how many of those secondary infections are produced. So here, if an infected bird is introduced into my mosquito population, this proportion right here of mosquitoes are actually going to also become infectious. Vice versa with the infected mosquito. If I put an infected mosquito inside of the bird population, I have this many birds becoming new infections. And so these are important when I start my simulations and I start modeling what's happening to my bird population as West Nile virus is introduced into its system. So here are some values. Like I said, blue jay and American crow are the two birds I'm analyzing. And this is taken from the CDC website and some West Nile virus references. And here I want to pay attention to these R naught values. And you see how they're greater than 1. So basically, the R naught equal to 2.79. That's about 3. So an infected American crow can infect 3 more of American crows. So from 1 infection, 3 more of those will be produced. And for the blue jays, they're a little more susceptible. They got a little bit less, but not by much. They can infect also about 3 more blue jays. And so West Nile virus is extremely influential on these two populations. And so what I plan to do with this, and I want to take these two populations and I want to simulate what's going on. Whether their populations are at an epidemic when West Nile virus is introduced into their system, or what's going on. And when you look at the CDC website, you can see all the different states, and it'll tell you how many cases are in all the different states. And Colorado, as of 2012, has become at an epidemic state for West Nile virus. And it's most likely due to increase in temperature. And as you can see from the 2012, I had 131 cases. Now, some of those cases are actually not even documented. And so that causes some discrepancies in my table, but that just means there's more cases that are just not documented. So there's more than what we know is going on. And that's my deal. Does that sound good?
Any questions?
Yes.
So that last thing that you said about the undocumented cases
Yes.
being included in the table, can you clarify that?
So my table, as I showed up here, I showed this table, right, from 2002 to 2012. Now, in Alamosa, we had 1 case produced last year, but there were a couple cases that weren't documented through doctors, and that's just among the town. There were a couple, and you know, people all the time, they don't go to the doctor and they don't care to get diagnosed with something, and they don't want that personal information released, and so some of that stuff's not accessible to us. And so that causes some discrepancies in the values I give, but that only causes a discrepancy in terms of I'm giving you less than the amount that's actually probably
These are the
there.
official ones
Exactly.
from the CDC.
Yes.
Because people will say, oh, I'm sick, I
Exactly.
must have West
These
Nile
are
virus,
official
but they're
values.
not doctors who
Exactly.
are self-diagnosing. Okay.
Any other questions?
Thank you.
Oh, go ahead. You can go ahead.
Well, because I'm interested in the mosquito control district.
Yes.
And some communities in Colorado have mosquito control districts and some do not.
Yes.
And I was doing some research similar to this last year, and I learned that for example, in Loveland and in Fort Collins, one is a mosquito control district, one does not.
Yes.
There was a higher outbreak in the mosquito control district. Did you look at anything like that in terms
I
of
haven't looked in
spraying
terms
pesticides
of
or
that. I have done a little bit of research on how they determine how many mosquitoes are infected, and they do it by sampling, but other than, I know Boulder also has a mosquito control. I haven't really looked into why as to more cases are produced in those mosquito controlled areas as opposed to the
One speculation is that when you treat for
when you use the pesticides, they use pesticides to try and regulate that, but it's not really
the resistant
Exactly.
mosquitoes are stronger. They're the super mosquitoes because they maybe 1% of them might survive being treated.
Exactly.
But they're the ones who are going to breed.
Well, and even when they do breed, they produce hundreds of mosquitoes, hundreds. And so when they're producing with that strong gene, they're gonna be passing that on, and so you're gonna have more mosquitoes that aren't going to be able to fight back that pesticide.
Did you interview Dr. Bill Britton at all for this?
No.
Okay. Who's an epidemiologist? I mean, I think this is fascinating. And
Yeah,
excellent
it's
research
in.
that
It's.
you've
I
done.
love this topic. It's
But
awesome.
he did happen. I talked to him about that one case from last year, and that was a person who had spent the summer in Texas. So
Yes,
most likely that
and-
person contracted the disease there,
Exactly.
but counted in our statistics. But
Exactly.
that's-
Like I said, at the CDC website, you can look at different states and all the different cases and all their different subcases. And Texas is actually at the worst state for West Nile virus right now. They are horrid. They have these very nice graphic representations of the United States, and they have these states what are called blackout states, and those states are considered to be at the epidemic state. And Texas has been in that blackout state for years. Okay. Any other questions? All right. I'd like to thank you for coming. I want to thank you guys for allowing me the opportunity to present some of my research. I am giving my senior presentation at the MAA meeting held on April 27th. It'll have a lot more mathematics involved, but you'll see some simulations on some of the work I've been doing. So I invite you guys to come.